Okay, so do you have any questions before we begin? We continue our discussion on the capacitors and capacitance. Now, the basic idea of capacitance was that if you have any charge distribution, let's say you have a system that has a total charge Q, okay, you have a system that has a total charge Q, so we already know that the potential of this system will be given by sum of terms of the form 1 over 4 pi epsilon 0 Qi over Ri j, let's say. And the electric, so if you just double the charges, if the charges are doubled, in that case, we know that the potential is also doubled. Well, this basically tells us that given a charge distribution, the potential should be proportional to the charge of the system or the charge separation, whatever you use to specify your system. And this proportionality constant is what we define as the capacitance of the system, of a given system. Now, we had already studied some examples. So if you want to calculate the capacitance of a given system, the only thing you need to do is just separate the charges somehow or put some charge. Separate the charges in your system such that the positive charges are on one side, negative charges on the other side. Calculate the potential difference that this creates, and then you have the proportionality constant, which is the capacitance. We did a few examples of this. One of them was this parallel plate capacitor, which was the simplest example. So if you just review what we did in the parallel plate capacitor, we know that the electric field inside in between the plates is just a constant. So the potential difference between these two plates is also a constant proportional to the charge density in each one of the plates. But the charge density is nothing but the charge over the total area. So we saw that the potential difference between these two plates is nothing but the charge in one of the plates multiplied by some constant, which we identified as the capacitance. Now, we did the same thing for this cylindrical capacitor, where instead of having two flat plates, we had two cylinders, one inside the other one. And again, what we did was we just carried some charge from one plate, put it on the other plate, calculated the potential difference. To calculate the potential difference, we first had to evaluate the electric field. Once we have the electric field, from the electric field, we could obtain the potential. And the potential was, again, proportional to the potential difference turned out to be proportional to the charge that we separated, and the proportionality constant, again, let us know what the capacitance was. Now, this is the general thing that you have to do in any system. Just take some charge from one part of the system, put it on the other part, calculate the potential difference. Well, in general, for a general system, you will not be able to calculate the potential difference. But nevertheless, you can measure the potential difference. So you measure the potential difference. If you know how much charge has moved from one part to the other part, then from one conductor to the other conductor, then you know what the capacitance of your system is. Now, there was one example which we didn't really study before. In all the examples we had, we mainly had two different conductors, and we were calculating the capacitance of this system. But even a single system, let's say if you spherical capacitor. If you have a sphere of radius, let's say r, it also has a capacity to store electric charges. So it is also a capacitor. So in this case, now in the previous cases we had these two conductors, we just carried charge from one conductor to the other one. In this single sphere example case, what we assume is we have a plus Q on the charge as well. We put some charge. Where does this come from? Well, we take it from infinity and put it on the sphere. So our second conductor is, in a sense, at infinity. So this is at infinity. And on there we have a minus Q charge. At infinity the potential is 0. So the potential here will be just the potential of our sphere. Well, we had already studied the sphere problem. We know that out of this conducting sphere, the system just behaves like a point charge. So right at where our sphere is, the potential is nothing but 1 over 4 pi epsilon 0 Q over R. This is the potential difference between infinity and the sphere. And this has to be Q over C, so the capacitance is nothing but 4 pi epsilon 0 times R. This is the capacitance of our system, of an isolated sphere. Now, any questions up to here? Whatever the system is, if you want to obtain the capacitance of the system, what you have to do is just put some charge, carry some charge from one conductor to the other one, and then calculate the potential difference by whichever means you can. And once you obtain the potential difference, you will see that it is proportional to how much charge you have carried from one conductor to the other one. It will be proportional to that one, and that proportionality constant is your capacitance. No, this is the capacitance of my sphere. This is the potential at this point, or you can say that this is the potential difference between the surface of the sphere, or between the sphere, any point on my conductor, and infinity. This is not the potential over here. This is a potential difference between the charges at infinity and my conductor. Other questions? Now let's also remember one more thing that we had discussed when we were discussing the potential. If you remember, when we had some many point charges distributed, let's say Qi, this is our system, and we talked about the electrostatic potential energy of the system. Do you remember the expression? This was the potential energy of my system is 1 over 2 sum over Qi times the potential at the point Ri. This was what we had obtained for the potential energy of the system. Now, a capacitor is the same thing. So let's say we have some conductor of an arbitrary shape. We have another conductor of another arbitrary shape. Now we know how to calculate the capacitance, at least in principle. You just put some positive Q charge on one of them, negative Q, so the other one is left with a negative Q charge. You calculate the potential difference. Well, since they are conductors, it doesn't really make sense to ask the potential difference between which 2 points. You just take any point on this conductor and any point on the other conductor. The potential difference is independent of which point you choose, because the conductor itself is an equal potential surface. All the points on this conductor have the same potential. All the points on this conductor have the same potential. So if you use this expression for the potential energy of my system, this is Qi V Ri, all my charges are either on this conductor or on this conductor. So this sum just becomes 1 over 2 sum over all the charges. Let's say this is conductor A, this is conductor B. Charges are on conductor A. Let me just put A times the potential of the conductor A plus 1 over 2 sum over B, the charges on conductor B, times the potential of conductor B. Now, the potential of conductor A is just a constant. The potential of conductor B is just a constant. I can just take them out of the summation sign. Now, the sum of all the charges in conductor A is nothing but plus Q. The sum of all the charges in conductor B is nothing but minus Q. So this will be the potential energy of this system is nothing but 1 over 2 times plus Q VA plus 1 over 2 minus Q VB, or 1 over 2 Q times VA minus VB, 1 over 2 Q times V. Well, remember V, when we were discussing the capacitors, V we used to denote the potential difference between the two plates of the capacitor. So this is the potential energy stored in this system. Now, of course, in your book you don't have this derivation. You have a different derivation. So now let's see how we can derive it using the derivation of the book. Again, we have our capacitor. You see, capacitors don't have to be regular shapes. They don't have to be parallel plates. They don't have to be parallel. Any two metals, any two conductor, or in fact, even a single conductor will be a capacitor. Of course, it will be hard to determine its capacitance. The only chance you have is to measure it. Even if you remember our discussions, your two friends over here form a capacitor. So we start from here. So to determine the capacitance or to charge them, what we do is we just take some charge from one conductor and carry it to the other one. So somewhere in between, the capacitor B will be charged minus Q, the capacitor A will be charged plus Q, and we are still carrying some charges. Now, if you want to carry an additional charge of dQ from capacitor B to capacitor A, we are charging the capacitor, how much work we have to do? So before that, let's see another thing. What is the potential difference? At this instant, what is the potential difference between capacitor A, the plate A and conductor B? So we know the capacitance. C is known. Q over C. At this instant, V is equal to Q over C. Now, what is the work done? How much work should I do if I want to carry an additional charge dQ from the conductor B to conductor A? dQ times V. But the amount of work that I do is nothing but stored in the internal energy of my system. So this work, this is the work that I have to do, is nothing but the change in the potential energy of my system. Now, at this instant, the charge is small q, so the potential difference at this instant is nothing but Q over C. So du, the change in the potential energy of my system, is nothing but dQ times Q over C. Now, assuming that I start from zero potential energy to some final potential energy, as I charge my system from zero charge to a final charge of large Q, so this equality should still hold. Why? You see, who is doing work? I mean, you should, whenever you are talking about work, you should always pay attention to who is doing work on what. You should never forget that. I am doing work. Now, the electric field is in this direction, from right to left. So I have to exert a force on the left direction. So I hold this charge dq, I'm moving it in this direction, so I have to exert a force in this direction. The displacement of the charge and the force that I exert on this charge is in the same direction. Of course, the electric field exerts a force in the opposite direction. The electric field exerts a force on this dq somewhere in that direction. The displacement is in this direction. So I am doing positive work, but the electric field is doing negative work on this charge. But the potential energy change in the system is the work that I do, assuming there is no kinetic energy change. No. I'm carrying this charge. I'm only talking about I took this dq and I'm moving this from negative charge to the positive charge. So that is the work we are discussing now. The charge is moving against the electric field. So this also tells me that U is equal to 1 over 2 Q squared over C, which is equal to 1 over 2. Since Q is equal to CV, this is Q times V. It's the same result. Okay. Well, that's basically what you define the capacitance as. I mean, of course, you can talk about putting some charge Q1 over here, some other charge Q2 over there. You can do that, but there's no point in defining anything called the capacitance for such a system. Now, the capacitance we always define as, well, I mean, in that case, you can just imagine that there is Q1 charge here minus Q1 charge over here, plus there's an additional charge over here. So you can just divide your system as if you have two capacitors. But I mean, that's kind of pointless, I would say. Other questions? Now let's apply this. Let's re-express this in terms of the electric field using for a parallel plate capacitor. This result is valid in general for every system. And well, you see, we started from assuming that we have just arbitrarily shaped conductors with arbitrary orientation. The only thing we need to know is that the potential and the charge is proportional, and the proportionality charge is what we define as the capacitance. But let's specialize now to the parallel plate capacitor. Now, we already know the capacitance of the parallel plate capacitor. Do you remember? A over D or D over A? A over D. I mean, if you have a larger area, you can store more charge, so the capacitance should be larger. V is equal to E times T, the magnitude of the electric field times the separation of the plates. And we know that the potential energy stored is 1 over 2 Q squared over C, or QV, or V squared over C. Now V squared times C. Yes. This is another expression for the energy stored. This is equal to 1 over 2 E squared times D squared times 4 pi epsilon 0 A over D. D just cancels, these two cancels. This is equal to 2 pi epsilon 0. Are you sure about this 4 pi? Well, let's see. The electric field inside the capacitor is sigma over epsilon 0 or Q over A epsilon 0. V is E times T. This is Q times D over A epsilon 0. So we don't have this 4 pi. One over 2 epsilon 0 A over D. 1 over 2 epsilon 0 E squared times A times D. Well, this is another expression for the energy stored in a parallel plate capacitor. Now, if you look at this expression, this A times D is nothing but the volume where E, the electric field, is non-zero. That's the only place where we have a non-zero electric field. Remember, if you have a parallel plate, the electric field is non-zero inside these parallel plates, and it is zero everywhere else. It is constant inside here. So this expression is in fact just another form of writing the integral of 1 over 2 epsilon 0 E squared integrate over all of space. It's the same thing. You can also write the potential energy for any system, in fact. Now, this is valid only for the parallel plate capacitor. If you have charges arranged as a parallel plate capacitor, then the potential energy of the system, electric potential energy of the system, you can write in this form. But for any charge distribution, creating some electric field somewhere in certain regions, maybe in all of the universe, the potential energy can always be also written like this, where we call this quantity over here UE is equal to 1 over 2 epsilon 0 times E squared is the energy density in the electric field. Now, if you go back to the other energy expression, we had this parallel plate. We said that U is equal to 1 over 2 Q squared over C, or U is equal to 1 over 2 epsilon 0 E squared times A times D. They are equal. At least in electrostatics, they are always equal. Now, why do we define such a density? What's the point? Does it have any significance? You see, now, if you look at this expression, the first one, and if I ask you the question, where is this energy stored? What would be your answer? Now, the first expression would tell me that the energy is stored in the charges. If I don't have any charges, I cannot have any energy. Now, we will, for example, later on when we study electrodynamics, we will see cases where we can have an electric field without any charge. We will have net charge equal to 0. Nevertheless, we will have some electric field. Now, if we stick with this first expression, it will tell us that if there are no charge separations in our system, then there is no potential energy. There is no energy stored in the system. Whereas the second expression will tell me that there is energy everywhere where there is some electric field. So even if you don't have any charges, somehow you manage to create an electric field without any charges, you will still have some energy stored in your system. So this energy will be the energy of the electric field itself. It will not be related with the charges. Now, at this point, these two are identical, because until now, whenever we have an electric field, we have some charges. Whenever we have charges, we have an electric field. So we cannot really separate these two. Up to this point, we can still treat the electric field as some mathematical stuff that we had invented just to visualize or to simplify certain calculations, simplify certain approaches. But eventually we will see that starting from this one, in fact, the electric field has its own physical significance, in the physical existence, in the sense that it has an energy. Now this tells me that the electric field itself, this second equation, electric field itself has energy. Just like an ordinary particle, if you take this mass, throw it, you know that it has kinetic energy, it will have potential energy. Now this equation tells us that the electric field also have some energy associated with the electric field itself, not with anything else. So this is the kind of one hint at the physical existence of the electric field. It's not just something we invented, some mathematical tool we invented. It exists in the sense that it has an energy. Later on we will see that it has its own momentum. So that's why, in fact, we are defining this energy density, because it's a property of the electric field, not the charges. It will have linear momentum. It even has angular momentum. That angular momentum you will be studying in your third year, but linear momentum we will be discussing about that. Now, this one tells us it has energy. Now, for the time being, we know that the electric field has energy of its own, without related to charges. This is why we are defining this thing. It's not producing energy. It has energy. I mean, you see, you cannot produce energy. You can convert energy. That's the only thing you can do. It has energy which can be converted into other forms of energy. No, it can be. Yes, we will see it later on. In electrostatics, whenever we have electric field, we have charges. But when we look at electrodynamics, we will see when we can have electric fields, although there is no charge separation. Yes, don't forget it. Other questions? Okay, this equation also tells us something else. If we don't go, just by looking at this, we can just read straightforwardly. Okay, we have these parallel plates. So in the parallel plates, the electric field is constant. It is independent of the separation of the plates. So if you separate the plates further out, D gets larger, the volume gets larger, so the energy stored in the capacitor increases. Although the capacitance decreases as we increase the volume, the energy stored increases. Okay, the formulas tell us that. So it's just this factor over here tells us that if D increases, E doesn't change, A doesn't change, so potential energy increases. Why? Can you give it a more physical explanation? Why does the potential energy increase? No, the magnitude of the electric field is constant. So the density of the electric field lines is the same. We are doing work. You see, we have this positive plate, we have this negative plate. If you want to increase the separation of the plates, you have to do work on your system. So the work that you do on the system is converted into the potential energy. Again, you are not creating energy, by the way. In order to do work, you have to use some kind of an energy. If you are actually just separating these plates, somehow you have eaten some breakfast and lunch, you have some chemical energy, you obtain that chemical energy, you are converting that into some mechanical energy of your arms, and which does work on this potential energy stored in the capacitor, and hence the potential energy of the capacitor increases if you are separating the plates. Questions? Now let's see connecting capacitors. Well, of course, when you have capacitors, eventually you would like to connect them to something. You want to make some use out of them. So this is whatever circuit you have that will use these capacitors. Let's imagine we have two capacitors. One of them and the second one. Now we would like to connect some of this over here. Which one would you like to connect here? Let's say this is C1. This has capacitance C2. Now this is whatever is at rest. So you have this black box over there where a wire comes out of that black box, and you will connect these two capacitors to that black box. What does the black box do with these capacitors? I don't know. Anything you can come up with. I just want to connect these two. So which one should I connect to this wire? Let's connect C1. Now what should I do with this end of C2? Should I connect it over here, or should I connect it over here, or can I connect it to somewhere else? Okay, that's one choice, but I mean, in that case, we are not connecting the capacitors. I would like to connect these capacitors. So how can I connect? Where can I connect it? This one end either here or here, or any other choice. Let me call that point C. Now this end, well, I can connect either to A or C. Let's connect it to C. Well, this is one choice of connecting. This is what we call the series connection. Capacitors in series. This will be the other choice. Or I can just I can connect this end over here and this end over here. This one also over here. This is what we call the parallel connection. And with two capacitors, there is nothing else you can do. These are the only possibilities we have. Either you connect one after the other one, or you can connect the same ends to the same points. And so that's why we only have two possibilities. Now, of course, if you have three capacitors, even with three capacitors, there's not much of a choice for you. I mean, some of them will be connected in series, some of them will be connected in parallel, but as the number of capacitor increases, you can come up with all kinds of weird connections. Just imagine that all of these lines have some kind of a capacitor attached to them. Yes. Well, some of them will be connected in parallel, some of them will be connected in series. And some of them will absolutely have no relation, neither series or parallel. Now, if you look at these two capacitors, they are definitely connected in series. Now, these two and this one are connected in parallel, but you cannot even say that this one and this one are connected in parallel, because there is also this one over there. This two is connected in parallel with this one. And well, you can consider some simplifications, but I'm sure certain capacitors you cannot even say whether they are in series or in parallel. So you can come up with all kinds of possibilities, but for two capacitors you only have these two choices. Nothing else. Now, of course, let's see. let's start with series capacitors. So you have one capacitor, let's say C1, and then you have another capacitor, C2. And let's call these points point A, point B, and point C. Now, what is the potential difference between points A and C? If you calculate the potential difference between point A and C, well, you can first go to A, then go to B. But if you first go to A, you get the potential difference between A and B. Then from B to C, you get the potential difference between B and C. So potential difference between A and C is nothing but the potential difference, the sum of these two potential differences. Now, one question is not really related with the capacitor in series, but remember how we define the potential difference. We said that, okay, VAC is equal to minus the integral of E dot dl from the point A to the point C. And we said that for any path going from A to C, this should be true. Any path, whatever you can imagine. Now let's see. What is the electric field over here? This point. I have my capacitors over here. They are of finite size. And I'm looking at the electric field over here. Now, we are always approximating the electric field over there to be 0. We said, okay, this is equal to 0. We said that, okay, we will be ignoring the fringing effects. So if we ignore the fringing effects, then the electric field is non-zero only within these places between the two plates only, and everywhere else it is 0. That's our approximation. But let's see, let's evaluate this integral from A to C along this path. So is there any place where the electric field is non-zero along that path? Only those 2 points. Well, 2 points do not contribute to your integral. So if the electric field outside the capacitors is exactly 0, then this integral is 0. So you cannot, there cannot be any potential difference between A and C. Because we already know that the potential difference between any 2 points is independent of how you go from A to C. But this also proves that this cannot be true, because I can just imagine another path, this one. I can also go around that path. There's finite electric field over here, a finite electric field over there, so there is a potential difference between A and C. It's not 0 as stated over here. Now the problem here is that, remember, E is equal to 0 only if we neglect the fringing effects. So this is basically an example where the fringing effects have to be there. I mean, we can neglect it in most of the times. When we are calculating the capacitance, the expression we obtain is actually close to the real expression for real capacitors. But for example, if you look at such an integral to calculate the potential difference, the fringing effects have to be there so that the electric field out of the capacitors should be non-zero, because we can always consider a path that never enters the capacitor. And this integral over this path should have the same value as this integral over this path. So, no, which goes where? No, I mean, we didn't yet discuss the charges on these plates. I mean, when we discuss the charges on these actual plates, then repeat your question. Now, for the time being, we are just saying that let's just assume that there are some charges on these capacitors. Then there will be some potential differences between the capacitors. And the sum of the potential difference between these 2 points should be equal to this one. And it should have the same value whether you evaluate this integral along this red path or you evaluate it along this orange path. It should have the same value. But along the orange path, the only electric field we have are these fringing electric fields. So they shouldn't be exactly zero. They can be small, they can be negligible, but remember, although the electric field can be negligible, we are taking a very long path. So they should be, electric field gets small, the path gets long, so their total effect shouldn't change the result of the integral, whether we go along this short path or along this very long path. We should get the same result. Questions? Okay, then see you after the break.